Okay, so it seemed like people were pretty lost in class today, and I thought that I would try to explain a couple of things to help out with the homework. This is all courtesy of Dr. Hun, so thank you, Lauren, for this. So I'm just going to start out in a really basic place, and hopefully some of you are going to know this, some of you might not. It's obviously totally okay either way. So if we all think back to like high school algebra class, we have this formula where it's y equals mx plus b, and we all remember that this is our constant, this is the y-intercept, and this is going to be kind of like our slope. So when we start doing logistic regression, we're actually looking at a pretty similar formula, but instead of the things that we're used to seeing, it becomes the logit of pi equals our alpha value, which is also a constant, like this b here, plus beta 1 plus beta 1x, plus beta 2x, and so on and so forth. So we're going to do just kind of a really simple model here to set this up and hopefully make it clear what on earth we're doing with this interaction term. So let's try a model where we're going to have our x, we're going to have sort of our x1 equals BMI, our x2 is going to equal sex, and our outcome that we care about is going to be diabetes, or risk of diabetes, basically. So in a simple model, or a more simple model than the ones that we were talking about in class today, we just have this constant plus beta 1 times sex plus beta 2 times, and I just got them backwards, but this should, can you tell it's been a long day? This should be BMI, and this should be sex. And in this equation, we're going to be able to pull our constant, our beta 1, and our beta 2 from the table that we get out of this data output, and none of those are going to be changed, and these are called main effects. So the beta 1, beta 2 with the BMI and sex are main effects. So what we might end up with at the end of the day is something like sort of like your odds of developing diabetes, or your log odds. And then that's going to be equal to, I'm going to make up some numbers here, everybody bear with me. So 0.5 might be our constant, and then let's say 2.9 times whatever the BMI value is, plus 1.3 times sex. Obviously I need to learn to write further over. So this is a simple model. These things can be pulled out of the stata output, and the numbers that come in front are basically what we're going to do is we're going to multiply them out, and we're going to end up with like 0.5 plus 2.9 times, let's say somebody had a BMI of 25, plus 1.3 times 1 for being male, and we're going to end up with a log odds risk here. So I'm not going to bother to do out the math, but this is kind of the idea behind this equation. So now let's do one that's a little bit trickier that's going to have an interaction. So we're going to basically do the same thing. So we're going to have logit of pi equals our constant term plus beta 1 BMI plus beta 2 sex plus beta 3 BMI times sex. And this right here, I'm temporarily just blocking it off, is our interaction. Again, need to leave more room. So when we have this interaction term in here, what happens is that we can't interpret the main effects alone. So that would be beta 1 for BMI and beta 2 for sex. And this interaction term is basically the difference in log odds. So if we were going to think about this, what it would be is the difference in log odds ratios for a 1 unit increase in BMI for males versus females. This is what this means. That's kind of complicated. We have not gotten that far yet, so you might not need to worry about it too much. But what we are going to worry about, basically, is how to deal with this interaction term kind of using algebra in the way that we've been subtracting in class and doing on the board, and everybody's kind of not having a lot of fun with. So we have these two variables, our x variables, and we're going to say that BMI can either equal 0 or 1. So it's either going to be, you know, like high BMI or low BMI. And sex is, again, going to equal 0 or 1. So when we plug this into our model, we're going to take our model here and we're going to look at a certain situation. So let's look at a situation where BMI equals 1, high, and sex equals 0. So maybe that means that you're female. So when we start doing this, we're going to have our first equation. So it's going to be our constant variable again. So we're going to have times beta 1, and then our BMI is equal to 1 because it's the high group, plus the beta 2 is going to be equal to 0, plus beta 3 is equal to 1 times 0. And then what we're going to do is we've got this equation here, and that's our equation for this particular scenario right here. And we're going to subtract off what's called the null equation, which is the equation where both of these things are equal to 0. So we're going to have beta 1 equal to 0 plus beta 2 equal to 0 plus beta 3 being equal to 0 times 0, so obviously 0. So then what we're going to do is we're going to go through and we're going to cancel things out. So we're going to cancel out the alphas because alpha minus alpha, obviously 0. Anything times 0 is 0, so we can get rid of all of these different things. Yay! And we're left with equals beta 1. And this kind of makes logical sense, right? Because if we have a 0 in our interaction term, we have no interaction term. The interaction term goes away. And so we're left with just caring about BMI, which we can get that BMI value and pull it just like we did up here. It's going to be 2.9. It's not going to change because there is no interaction impacting that main effect term. And the exact same thing is true if we were to do the reverse. We were to make sex 1 and we were to make BMI 0. We were to plug all of this in. We would end up with beta 2, and beta 2 would be equal to 1.3, my made up number here, which is the exact same thing that it's in the main model because, again, there's no interaction term impacting it. So where this starts getting a little bit complicated is when you have a 1 and a 1. So I'm moving my paper away. So we're going to say BMI equals 1, sex equals 1, and then we're going to do this equation again. So we have our constant term here, and then we're going to have beta 1 times 1 plus beta 2 times 1 plus beta 3 times 1 times 1. So that's going to end up being 1. So this is our like high group. And then we're going to subtract off the null again. So we have our alpha, beta 1 times 0 plus beta 2 times 0 plus beta 3 times 0. I think I need one. Yeah, I need one more parentheses there. So what ends up happening here is that this kind of all goes away and our alpha goes away because they're zeros. Yay. I love being able to cancel zeros. But what we end up with, rather than that nice beta 1 or beta 2, is beta 1 plus beta 2 plus beta 3. And this is showing that the interaction of these two effects has an effect on the main effects, which I just used the term effects a few too many times in one sentence, but it's basically showing that the interaction is doing something to the coefficient in front of these variables. So when we add them all together, you know, if we were to add our 2.9 plus 1.3 plus whatever beta 3 happened to be, I didn't write it out in the original model, let's say it's like 3.1. If we were to add all these things together, this gives us a new value that shows us what happens when we have the interaction term in our model. So what do you do when you're looking at something where you have like where you have more than 2 levels of something? So you have like 3 levels of BMI. So one thing that you can do is you can do BMI equals like 0, 1, 2, and you can still do this algebra out, and it's actually pretty easy to do, and it's not super hard. The other thing you can do is you can kind of set up dummy variables, and this is what we were talking about doing in class. So for example, the example we were using in class is overweight or obese, and then, you know, it's like less than 25, 25 to 30, 30 plus. I think those are the right categories. So what happens here is that you can either be in one of these categories or the other. You're either overweight or you're obese. And that logically doesn't make a whole lot of sense. I get it. But if you go to the if you think about it, if you go to the doctor, or you are a doctor, as some of the fabulous people in our class are, you don't tell a patient, well, you're obese and you're overweight. You just tell the patient that they're obese. So in this case, we're going to put, you know, a 1 here, a 0 here, and a 0 here. Those are dummy variables. And then in this case, since you can't be obese if you're overweight, we're going to have zero variables, and our under 25 is going to be our reference group, so that's 0, 0. And then you can start plugging these in to compare sort of like, so beta 1 times, oops, I need my alpha, alpha plus beta 1 times overweight, plus beta 2 times obese. And you're not going to end up with the nice, clean things that you ended up sort of with our original equations where you had like just beta 2. But what you're doing is you're looking at the change in risk between someone who is obese and someone who's overweight and someone who's obese. So typically you would do the obese subtracting the overweight, since that's the lower risk category. So basically by doing that, you're able to make that comparison, and there's not really another way to do that, I mean, aside from the stata commands. So that's the sort of logic behind doing this crazy mathematical algebra that makes absolutely no sense. What you're basically trying to do is to be able to compare reference groups. So hopefully this all makes a little bit more sense. And at the end of the day, what we're going to end up with is a really crazy model. And I'm gonna make some stuff up here, but we're going to have our constant term. So we'll just keep that as 0.5. And then you're going to have a coefficient in front of all of your variables, which is what we're trying to get stata to give us. So, you know, let's say it's like 2.9 times BMI, and I'm, again, totally making up numbers, 3.3 times age, and plus 4.1 times, maybe we have a like healthy diet variable, plus 5.2 times activity level, plus 1.2 times family history. And what all this is going to add up to when we plug in the numbers, for example, for an actual human being, we're going to get a model where, like, if somebody had a BMI of 25, they were 20 years old, they ate a really healthy diet, and we had a score for that. So let's say that 1 is the healthiest diet you could have. They were also really active. 1 is the most active you could be, and they did not have a family history. Then we would end up getting an odds ratio comparing them to the reference group of 0, 0, 0, 0, 0, that tells us how likely they are to develop diabetes, or to, if you were doing a different way of thinking about it, potentially to have diabetes. So hopefully that makes sense as to what we are trying to model, and hopefully that also makes sense as to why we care about all of this weird algebra. So I hope everybody has a fantastic weekend, and I apologize if this is lengthy and not very fun. So please just email me if you have any questions. I sent out Dr. Hun's notes, and hopefully those will be helpful to people as well. So have a fantastic weekend and a good rest of your evening. And I'm going to try to figure out how to make this stop recording.